In this lecture, we will cover resistive circuits. After covering the basics of circuit drawings, we will learn Kirchoff's current and voltage laws, then series and parallel resistors, and then we will learn how to solve circuits using equivalent circuits. Let's assume a circuit consists of two parts, part A and part B. If we replace the part B with an equivalent circuit, B equivalent, that does not change the voltage or current of any element in circuit A. In other words, if you would have a resistor network in the part B, we can reduce this resistor network to a single resistor, and the behavior of the circuit from the perspective of part A will not change. We will use this principle to solve some of the electrical circuits. How does an electrical circuit look in real world? Here we see a breadboard, and on top of that breadboard an electrical circuit is implemented, and as it is the case in most of the times, it looks like a mess. On the left side of the screen we see a printed circuit board. Most of our electronic devices have the components on these type of printed circuit boards. And on the right side, we see the corresponding circuit schematic in the software. This printed circuit boards consists of multiple layers, and that way allow lots of components to fit in a dense manner to a small area. A circuit can be drawn in many ways. In general, the cables are not straight, and we can consider to draw the circuit as we see the cables with curves. But in general, as a convention, we use horizontal and vertical lines. Two circuits are the same if the following conditions are true. There is one-to-one correspondence between the nodes of the drawing. For instance, here we have this node, and that same node is here. There is one-to-one correspondence between the elements of the drawing. All the elements here in this drawing is present in this original drawing as well. And corresponding elements are connected to the corresponding nodes. For instance, this element 1 is connected to the node A and B. And similarly, that element here is connected to the same nodes. Therefore, we can tell that A is equivalent to B, which is equivalent to C. We use horizontal and vertical lines, sometimes also diagonal ones, such that we can understand the connections of the elements easier. In 1847, Kirchoff from the University of Berlin formulated two laws which are now the foundation of the electrical circuit analysis. The first one is Kirchoff's current law, which states that the algebraic sum of the currents into a node at any instant is zero. The second one is Kirchoff's voltage law. The algebraic sum of the voltages around any loop in a circuit is zero for all the time. Let's see how Kirchoff's current law and Kirchoff's voltage law works. Let's focus to this node. Which currents are entering this node? Plus 7 amperes, minus 4 amperes, and here we see 3 amperes is getting out. In other words, minus 3 amperes is entering to this node. So I just write here minus 3. And when I sum these, I end up with 0. So in other words, Kirchoff's current law is holding. Let's look to the Kirchoff's voltage law for another loop. Let's focus to this loop. In this loop, we have plus 4 volts, minus 0 volts, and again we have plus minus 4 volts. When we add this, we end up with 4 minus 4, 0 volts. In other words, Kirchoff's voltage law for this loop is holding. Let's do an example using Ohm's law and Kirchoff's laws for circuit analysis. We need to find each current and voltage in the circuit, given that R1 is equal to 8 ohms, V2 is equal to minus 10 volts, I3 is equal to 2 amperes, and R3 is equal to 1 ohms. In addition, we need to find the value of the R2. It is always good to start solving these problems if we know what is known. R1 is known, V2 is known, I3 is known, and R3 is known. So we need to start writing Kirchoff's voltage law and Kirchoff's current law equations. Let me start from this upper loop because I know the voltage supply voltage 12 volts. I know the value of V2. The only unknown is V3. Let's write and see whether we will be able to find V3 here. I start from plus 12. 12 minus V3 plus V2 is equal to 0. Since I know the value of V2, I can write this equation as 12 minus V3 minus 10 is equal to 0. And if I solve this for V3, I end up with V3 is equal to 2 volts. So I found the first unknown, V3. Let's try to write another Kirchoff's voltage law for this loop now. So I start from V3. V3 minus 10, because the arrow enters from the minus part, plus V1 is equal to 0. Since I know V3, I write 2 minus 10 plus V1 is equal to 0. Accordingly, when I solve this, V1 is equal to 8 volts. So now I know V1 as well. How can I find the other variables? I know V1, V2, and V3. I can try to write the Kirchoff's current law for this node A. For node A, the Kirchoff's current law would be I1 minus I2 minus I3 is equal to 0. Among these, I know I3, but then I need to find I1. Can I find I1? Yes, because I know both V1 and R1. So I1 will be equal to V1 over R1. V1 value is equal to 8 volts divided by R1 value, which is 8 ohms, which will result in 1 amperes for the I1. Now, since I know I1 and I3, I can just solve this equation. 1 minus I2 and minus 2 is equal to 0. Accordingly, I2 is equal to minus 1 amperes. So now I have I3, I1, and I2. So I know all the currents in the circuit as well. The question also asks us to find the value of R2. R2 will be equal to simply V2 divided by I2. And when I plug in the values of V2, which is equal to minus 10 volts, divided by I2, which is equal to minus 1 amperes, I end up with 10 ohms as the value of R2 in this question. I can also go and find the values of R1 and R3 just to double check whether I did this question right or wrong, but I will not do those right now. In this example, we need to find the current measured by the ammeter. In other words, we need to find the current which is flowing on this branch of the circuit. Noting that the ammeter acts as a short circuit, we can redraw this circuit by removing the ammeter and by connecting it just by a wire. So how will we solve this circuit now? How will we find IM? I can do this by writing the Kirchoff's current law for this node. Apparently, 3IA is flowing downward, IM is flowing this way, and if I extend this IA is also flowing outward. So I can write the Kirchoff's current law as minus IA minus 3IA minus IM is equal to 0. Accordingly, I can write IA is equal to minus IM divided by 4. Secondly, I can try to write a Kirchoff's voltage law, and I can write it on these small loops, but maybe I can this time write it for the big loop around the circuit. Let's assume that here over the 4 ohm resistor I have minus plus 4IA. Over this 2 ohms I have plus minus 2IM. I put the plus and minus signs based on the directions of the currents. Let's write the Kirchoff's voltage law. Minus 4IA plus 2IM minus 12 is equal to 0. I can substitute for IA minus IM over 4. Minus 4 times minus IM over 4 plus 2IM is equal to 12. So here I end up with 3 times IM is equal to 12, and at the end I solve IM as 4 amperes. In other words, the current measured by the ammeter will be equal to 4 amperes. For different special configurations of resistors, we can come up with some certain rules. Voltage division rule is one of those. Let's derive it together. So let's try to write the Kirchoff's voltage law for this loop. V1 plus V2 plus V3 is equal to Vs. Let us try to write V1 using Ohm's law. V1 is equal to R1 times I1. Similarly, V2 is equal to R2 times I2. And V3 is equal to R3 times I3. Let us plug in these V1, V2, and V3 inside the first equation. We will end up with R1 times I1 plus R2 times I2 plus R3 times I3 is equal to Vs. Let us try to write the Kirchoff's current law for this node A. I1 is equal to Is. Similarly, I2 is equal to I1. And similarly, I3 is equal to I2. So then I can write the equation 2 as R1 plus R2 plus R3 times Is is equal to Vs. Accordingly, Is is equal to Vs divided by the sum of the resistors. Now let us try to express one of the voltages. V1 is equal to R1 times Is, which is equal to Vs times R1 divided by R1, R2, and R3. So I can show the voltage V1, the supply voltage times the division of the resistor divided by the series resistor of the whole circuit. So this is the series voltage division rule. Now we will use the voltage divider rule for a design problem. We need to find the values of R1 and R2 for the following technical specifications. The input and output voltage are related by V0 is equal to 0.8 Vs. And secondly, the voltage source must not supply more than 1 milliwatt when the input to the voltage divider is 20 volts. Okay, let us see one piece of information which I know is V0 is equal to 0.8 Vs. Using the Kirchoff's voltage law, I can write that V1 is equal to 0.2 Vs, and from the voltage divider rule, then I can come up with 4 times R1 is equal to R2. In addition to this, I have another piece of information. Power supplied by the power supply is equal to Is times Vs. I know that Vs is equal to 20 volts and power should be 1 milliwatts. Accordingly, Is is equal to 1 milliwatts divided by 20 volts. Now I need to just have a good grasp of the SI prefixes, and the resulting value is 50 microamperes. It is a small amount of current. Now from this, how can I go to the resistor values? The R1 plus R2 times Is should be equal to Vs. Accordingly, R1 plus R2 is equal to 20 volts divided by 50 microamperes. Micro means 10 to the power of minus 6. So accordingly, here we have 400 kilo ohms for R1 plus R2. From equation 1 and from equation 2, I can write that 5R1 is equal to 400 kilo ohms, and I find R1 is equal to 80 kilo ohms. Using equation 1, I can find the value of R2 as 320 kilo ohms. By finding these R1 and R2 values, I conclude my design problem. Circuit elements, resistors, capacitors, inductors, etc. are connected in parallel when the voltage across each element is identical. Let's look at this example. Here I have R1 and R2. Both of them are connected to the same nodes A and B. Therefore, they are in parallel and both of them have the same voltage. Let us try to analyze the circuit using KCL, KVL, and Ohm's law to see whether we can reduce these two resistors to a single equivalent resistor. Let's start by writing the Kirchoff's current law for the node A. Is is equal to I1 plus I2. Now let us write some additional equations. I can write Ohm's law easily. V is equal to I1 times R1 and V is equal to I2 times R2. From these equations, I can get I1 and I2. I1 is equal to V over R1. I will denote this as 2. I2 is equal to V over R2. I will denote this in as 3. And I will denote this first equation as 1. If we substitute I1 and I2 in 2 and 3 into the equation 1, I end up with Is is equal to V over R1 plus V over R2, and I can write this into the parentheses of V as 1 over R1 plus 1 over R2. Now if I want to find the equivalent resistance, I need to find V over Is, and V over Is is equal to 1 over R1 plus 1 over R2. So basically I can reduce these two resistors to this equivalent resistance, which is also sometimes denoted as R1 in parallel to R2. For the circuit below, we need to find the equivalent circuit, the current and voltage in each branch. Let's look at this circuit. We have 3 parallel resistances, and in this case, it might be worthwhile to use the transconductance. Let's remember this concept. V is equal to R times I is the Ohm's law. We can write this as I is equal to G times V, where G is the transconductance and is actually 1 over R with the units of Siemens. So accordingly, we can write G1 is equal to 1 over R1, which is equal to 2 Siemens. G2 then will be equal to 4 Siemens. And G3 will be equal to 8 Siemens. Now, when we write this, I can just write these equations. I1 is equal to G1, which is 2 times V. I2 is 4 times V, and I3 is 8 times V. Then I can write the Kirchoff's current law for this node. 28 amperes is entering, and I1, I2, and I3 are getting out. I1 plus I2 plus I3 is equal to 28. If I use these equations and put them inside this last Kirchoff's current law equation, I end up with 14V is equal to 28. From here, I find the V is equal to 2 volts. Then, in order to find I1, I simply use this equation here. 2 times 2 volts is equal to 4 amperes. For I2, I use the second equation, and I end up with 8 amperes. And I3 will be accordingly 16 amperes. And if I add 4, 8, and 16, I end up with 28 amperes, which is the amount of current supplied by this source. So I found the voltages, I found the currents, and the equivalent circuit can be drawn as this. G1, G2, and G3, if I add them, I end up with G equivalent is equal to 14 Siemens. And accordingly, R equivalent for the circuit will be 1 over 14 Siemens, 1 over 14 ohms. And then I will have a current source, which is 28 amps, and a single equivalent resistor, which is 1 over 14 ohms. And this will be our simplified, reduced equivalent circuit. Voltage sources connected in series are equivalent to a single voltage source. Specifically, the voltage of the equivalent voltage source is the sum of the voltages of the series sources. For instance, here in this example, we have VA and VB. They have the same polarity, plus minus and plus minus. The equivalent circuit is a single voltage source with the voltage VA plus VB. In the second case, we have VA with the positive minus polarity and VB with the opposite minus positive polarity. And the resulting equivalent circuit is VA minus VB as a single voltage source. However, we cannot do the same thing with the current sources, because we just need to write the Kirchoff's current law, and in this case, IA should be equal to IB, and therefore two different independent sources cannot be connected in series. In this exercise, we need to write the equations for the circuit using KCL, KVL, and Ohm's law. And we observe that we have two voltage sources connected in series, VA and VB. Our first step should be to combine these voltage sources. When we combine these voltage sources, we end up with a single VS, which is equal to VA plus VB. Let us start with writing KVL equations. Firstly, for this loop. Vs plus V2 is equal to V1. Then for this loop, since both Vc and V1 are in parallel, V1 is equal to Vc. Similarly, for this loop, we have V2 is equal to V3. Let us now try to write the KCL equations. Firstly, for this node, we have IC entering, I1 exiting, so therefore with minus sign, and IS exiting that node. So our equation is IC minus I1 minus IS is equal to 0. Similarly, I have one more node here. IS is entering, so I write the positive sign. I2 is exiting and I3 is exiting, so this is another equation for the circuit. Then I can also write Ohm's law. For instance, here I have V1 is equal to R1 times I1. I have V2 is equal to R2 times V2. I2. And similarly, V3 is equal to R3 times I3. So now I wrote all possible equations which I could write about the circuit. Indeed, I can write one more loop which is for the whole circuit. Let's try to write this together. Vs, another KVL, Vs plus V3 is equal to Vc. Alright, in this example, we need to determine the resistance measured by the ohm meter. We will do this by reducing the resistances using series and parallel resistance rules. In the first step, I observed that 60 ohms is in parallel to 30 ohms because they are both connected to the same nodes. They are connected to A and B. So the resultant circuit will look something like this. 60 ohms in parallel with 30 ohms, whatever that value is connected to a 20 ohm resistor. And here I have a 10 ohm resistor. And I measure the resistance from these output ports. So our equivalent will be 1 over 60 plus 1 over 30, which is equal to 1800 divided by 90 and 20 ohms. This should be correct because the resulting resistance is less than both the initial resistance of 60 and 30. In other words, we just have more options for the current to flow, therefore the resistance is lower. Now let us go one more step. How can I reduce this circuit? My circuit becomes 20 ohms, another 20 ohms here. Here I have 10 ohms, and I measure my resistance from these ports. I observe here that this 20 ohms is in series with this other 20 ohms. Therefore, the equivalent resistance is 40 ohms. So I can write the circuit as a 40 ohm resistance and a 10 ohm resistance. Since both of them are in parallel, I can follow the parallel resistors rule once again to find the equivalent resistance of the circuit. So R equivalent to what we will see measured by the ohm meter will be 1 over 40 plus 1 over 10, which is equal to 400 divided by 50, and is equal to 8 ohms. The result of this question is 8 ohms. Current sources in parallel are equivalent to a single current source. Here I have IA and IB are flowing in the same direction, and the resultant equivalent circuit is a single current source with IA plus IB amount of current. Similarly, here I have IA flowing upward and IB flowing downward, and therefore the resulting current source is having the value of IA minus IB. If I would have drawn this with the arrow pointing to the other direction, then I would have the current value as IB minus IA. We cannot do the same thing with the voltage sources, because when we have two parallel voltage sources, the value of VA should be equal to value of VP. Therefore, I cannot have two independent voltage sources in parallel. In a circuit, whenever I see two current sources in parallel, I reduce them to a single current source by adding these current values. Here we have two sources and they have been reduced to a single source. In this example, we need to find V out, and one way to analyze these circuits is replacing a set of resistors with an equivalent resistance, and thereby reducing the network to an easier form. Let's solve this example. Here I can start solving this circuit by reducing R1, R2, and R3 to a single or equivalent resistance. These are in series and they have the 1 ohm value, so the resultant resistance will be 3 ohms. 4 and 5 are 6 ohms and they are in parallel, so I can reduce these two by finding the R4 in parallel R6, and this will be equal to 1 over 1 over 6 plus 1 over 6. If the resistance values are equal, then I can simply divide them by 2, so the result will be 3 ohms. And now, after I have here the 3 ohms, I can do the same operation with the R6. 3 ohms in parallel with R6 will be equal to 1 over 1 over 3 plus 1 over 6, which will be equal to 18 divided by 9 and 2 ohms. So this whole circuit accordingly reduces to this form. I have the voltage source Vs, which is equal to 12 volts. Then I have one equivalent resistance, this one, which is 3 ohms, and another resistance over which I will be measuring the plus minus V out, which has the reduced value of 2 ohms. Using the voltage divider rule, I can calculate V out as Vs times 2 ohms divided by 2 ohms plus 3 ohms, and accordingly this will be equal to 24 divided by 5 and 4.8 volts. So we found the voltage over R6, which is equal to voltage over R5 and voltage over R4, since they are all in parallel, which is equal to 4.8 volts. Here we have a current source IS and a resistor network in parallel to this current source, and we need to find the current I1 passing through the 3 ohm resistor. We can do this by reducing the resistor into a single equivalent resistor in parallel with I1. So how can I start? I first observe that R2 is in parallel with R3, and I can reduce these two. R2 in parallel R3 will be equal to 4 ohms. How did I do this without any calculations? I know that both of them have the value of 8 ohms, and in this case I just divide their value to 2. in order to find the equivalent parallel resistance, 4 ohms. And I observe that R4 is in series with this 4 ohm resistor. So the resultant resistor will be R4 plus 4 ohms. Since R4 has the value of 2 ohms, the resulting resistor will be 6 ohms. So this is 6 ohms. 6 ohms is in parallel with 18 ohms. So I will reduce these two. 6 ohms in parallel with 18 ohms. This will be equal to 1 over 6 plus 1 over 18, which is equal to 6 times 8, 108, divided by 24. And this will be, if I'm not wrong, 4.5 ohms. 4.5 ohm resistor between this node and that node, which is encompassing all of this part of the circuit, is in parallel with 9 ohms. 4.5 ohm in parallel with 9 ohms will be equal to 1 over 4.5 plus 1 over 9. 9 times 4.5, 40.5, divided by 13.5, and it's a beautiful simple 3 ohm resistor. So I solved right now this whole part of the circuit, and the equivalent resistance is 3 ohms. So the whole circuit have reduced itself to a single 5 ohm 5 ampere current source and 3 ohm resistor in parallel with a reduced 3 ohm resistor, and we want to find the current I1. So obviously, since both of these resistors have the same value, the current which will be passing through them will be the same. And here I have 5 amperes going this way. So I can write the Kirchoff's current law for this node, which will be I1 plus I2 is equal to 5 amperes. And noting that I1 is equal to I2, I1 will be equal to 2.5 amperes. So I solved this circuit mainly by reducing the equivalent resistances, but this I can do only in special cases. For instance, if this circuit would have contained more number of current or voltage sources or other elements such as dependent sources, this trick would not have worked. A circuit consisting of n elements has n currents and n voltages, so we might have up to 2n unknowns for our equations for circuit analysis. By careful labeling, we can get rid of the trivial relations, and here are a set of guidelines for how to label these circuits and what type of simple operations to do when we start analyzing it. However, rather than reading these, I recommend that you should solve lots of different circuits, and you will learn what type of guidelines to follow by solving these exercises.